Black holes are the universe's most extreme objects. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. These cosmic monsters are formed when massive stars collapse at the end of their lives. The resulting object is incredibly dense. Its gravitational pull is immense. As matter falls towards a black hole, it is accelerated to incredible speeds. This is due to the intense gravitational field of the black hole. Think of a ball rolling down a hill. The steeper the hill, the faster the ball goes. Now, imagine a hill with infinite steepness. That's a black hole. These extreme speeds are what make black holes natural particle accelerators. In fact, they are the most powerful accelerators in the universe. They dwarf even the most powerful particle accelerators on Earth, like the Large Hadron Collider. Black holes accelerate particles to near the speed of light. This opens up exciting possibilities for studying the fundamental building blocks of matter. The event horizon is the boundary around a black hole beyond which nothing can escape. Once something crosses the event horizon, it is lost to the black hole forever. Not even light can escape its grasp. This is a point of no return. As an object approaches the event horizon, it experiences extreme tidal forces. These forces are caused by the difference in gravity's pull on different parts of the object. The side of the object closer to the black hole experiences a much stronger pull than the side farther away. These tidal forces become so intense that they can stretch and compress objects. This process is known as spaghettification. Imagine being stretched like spaghetti as you fall into a black hole. What happens to matter as it crosses the event horizon and falls into a black hole? Our current understanding of physics breaks down at this point. We need new theories to explain the extreme conditions inside a black hole. According to general relativity, all the matter in a black hole is concentrated at a single point at its center called the singularity. This point has infinite density and zero volume. It is a place where the laws of physics as we know them no longer apply. However, quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels, suggests a different picture. Quantum mechanics tells us that space-time itself is not smooth and continuous. Instead, it is granular, made up of tiny indivisible units. This granularity of spacetime could have profound implications for our understanding of black holes. Imagine trying to paint a wall with a brush that can only make dots of a certain size. You can never get a perfectly smooth surface. Similarly, the granularity of spacetime could prevent matter from collapsing to a single point. This is where the analogy of the painter's paradox comes in. No matter how much paint the painter uses, they can never fill Gabriel's horn, a mathematical shape, because it has an infinite surface area. Similarly, the breakdown of particles at the event horizon of a black hole could mean that they are never truly compressed to a point. If particles are broken down into these fundamental units of spacetime, they would release a tremendous amount of energy. This energy could be in the form of particles with incredibly small wavelengths, smaller than anything we can currently detect. These particles could hold the key to unlocking new secrets about the universe. Studying these particles could give us insights into the fundamental nature of space, time, and matter. It could also help us to understand the early universe, where conditions were similar to those found inside black holes. Black holes, these cosmic enigmas, may hold the answers to some of the biggest questions in physics.